Dear OMAE attendees, welcome to my talk. My name is Alyosha Sander. I'm a researcher at Bremen University in Germany. Before I begin, I want to extend my gratitude to all the people that made this project possible. Most notably, our partners from the industry, my colleagues, and of course my students. In 2019, we were investigating different approaches to offshore wind farm installations. To this end, we had developed and deployed a set of simple sensors aiming at recording accelerations experienced by turbine components during harbor operations. As access to the sensors, once the components were loaded onto the installation vessel, was restricted, our sensors remained aboard the ship. During the installation of the first turbine, large relative motions occurred. Because we had the sensors aboard the installation vessel, we quickly decided to investigate. The following video exemplarily shows these large relative motions. So, what do you think? Where are the relative motions coming from? Today, most offshore wind turbines are installed component by component, with the mating of the blades being the most crucial step. Fitting the blade bolts into the hub flange requires great care and precision, as damages to components can easily be inflicted. Let us consider the system we are trying to investigate here. The left-hand side shows the partially installed turbine. It consists of foundation, transition piece, tower, nacelle, and rotor hub. Both wind and waves inflict loads onto the structure, which in turn can cause motions of the turbine. The blade is locked into a lifting yoke, which in turn dangles from the crane hook. Here, the lifting yoke is referred to as single blade installation tool, or SBIT. Both blade and yoke are subject to wind forces. Considering the 3 degrees of freedom of the blade yoke assembly and the chaotic nature of the atmospheric boundary layer, it becomes increasingly difficult to predict the behavior of the blade during installation. With the question, where are the motions coming from and what can we do about it, at hand, we set out to measure accelerations at different positions of the turbines. While we measured different accelerations throughout the whole installation, in this talk we are only going to present a fraction of the results. We focused on motions occurring after the nacelle was installed, but before the blade installation starts, to better understand the general behavior of the systems. The overall dataset spans 32 turbine installations and will be made available in an upcoming publication. Here you can get a quick impression of the sensor devices. Devices consisted of a battery, the black cubic structure labeled A MEMS acceleration sensor, a GPS receiver, and a microcontroller, as well as an SD card for data storage. From the total of 32 installations, the first 16 were selected. The photos show various positions where sensors were installed. On the transition piece, the upper tower platform, and the helicopter hoisting platform, as well as the lifting yoke. After each installation, data from the sensors was retrieved and post-processed. Accelerations were either in fore-aft or side-side direction in the coordinate system of the turbine. To yield the position of the sensors and thus the turbines in space and time, accelerations were resampled, filtered, and numerically integrated twice. This results in the blue ball of wool-like structure that you can see in the middle of the turbine in subfigure A. GPS data was used to determine installation times. This is depicted in the upper right subfigure B. We calculated the deflection as a means of how much the turbine has been moved from its resting position. To better understand the correlation between the deflection and the environmental parameters, such as wind speed and wave heights, we calculated 10-minute means of the deflection, as well as the environmental parameters. These were then combined in scatter figures. Where appropriate, we fitted linear functions to the data to build simple models of turbine behavior. Here, you can see the metocean data from the selected time periods. All parameters shown are 10-minute mean values. On the left-hand side, the significant wave height as a function of the wave peak period is shown. A group of outliers with a peak period of about 8 seconds and a significant wave height of about 1.4 meters can be seen. These correspond to swell waves. On the right-hand side, the significant wave height as a function of the wind speed is shown. Additionally, the data points are colored by the wave peak period. The same group of outliers as in the left-hand figure can be observed. The orange data points with a wave peak period of around 8 occurred at wind speeds of less than 5 meters per second, clearly corresponding to the characteristics of swell waves. A linear function was fitted to the data to give an overview of the almost linear relationship between wind speed and significant wave height. The maximum significant wave height observed was 4.5 meters with wind speeds just below 25 meters per second. To give you an idea of what the deflection as a time series looks like, the red line corresponds to the instantaneous deflection from a randomly chosen turbine. Note that this time series spans several days. The deflection is given as normalized value, corresponding to percentage of tower radius. The white line corresponds to the 10-minute rolling mean of the deflection. The black line is the single blade installation limit. This represents a threshold above which the likeliness of a blade installation to succeed is diminished. This is, however, not a fixed value, but rather a rule of thumb. Maximum deflections go well above 6% of tower radius. Note that for an external observer, the magnitude of the motion would correspond to roughly double the deflection. To better understand the relationship between the deflection and the ocean environment, we constructed scatter plots. On the left, you can see the 10-minute mean deflection as a function of the significant wave height. Very few data is available where significant wave height is below 0.5 meters or above 4.2 meters. A linear function was fitted to the data showing a correlation coefficient of 0.72, thus rendering the relationship almost linear. On the right-hand side, the 10-minute mean deflection as a function of the wind speed is shown. Again, we fitted a linear function to the data, which also shows a mostly linear relation. On the left, the 10-minute mean deflection is shown as a function of the wave peak period. Additionally, the data points are colored by significant wave height. The swell wave event we saw earlier can be identified again. The increase of deflection with increasing wave peak period is much broader in comparison with wind speed or wave height. Here, deflections ranging from 1 to 6% of tower radius for a given wave peak period of 4.5 seconds can be observed. With an increase in wave peak period, significant wave height also increases. As we found the spreading of the deflection for a given wave peak period quite fascinating, we decided to normalize each data point by the linearly fitted function of the deflection. This normalization carves out the deviation of the observed deflection from the expected deflection. These expected deflections are, of course, the linearly fitted function, but the function is derived from the scatter data between deflection and significant wave height. By applying this normalization, values below 1 would indicate less than linear behavior for the observed deflection. Values larger than 1 indicate nonlinear behavior. This is shown on the right. As the wind can of course also influence the observed deflection, the data points are additionally colored by wind speed. For wave peak periods between 4 and 7 seconds, large deviations from the linear expected behavior can be observed. with an increase in wave peak period, the deviation is reduced to approximately 25% of the linear behavior. Clear peak for wave peak periods between 4 and 5 seconds can also be observed. Here, on the left, the same ratio of observed versus expected behavior is shown. However, this time as a function of the wind speed. Data points are colored by wave peak period. As in the previous figure, the deviation from the linear behavior is reduced with increasing wind speed. Again, a clear peak emerges for wind speeds between 4 and 12 meters per second. Removing data points where the peak period is larger than 6 seconds reveals a very sudden, step-like change in the ratio between observed and expected deflection. This is shown on the right-hand side. Whether this is due to measurement error or corresponds to a physical effect cannot be said. Let us quickly recap our findings. Measurements from the turbines reveal that indeed the turbines are, for the most part, causing the large relative motions observed during single blade installation. Deflections show mostly linear dependence on wind speed and wave height. The data presented here is but a fraction of the complete dataset, which will be published soon. While the quality of the sensors might be somewhat of an issue, these findings are a first attempt at measuring physical effects during offshore wind farm installation and, subsequently, might help improve single blade installation and thus reduce levelized cost of electricity. Thank you for making it through the video. Thank you for your attention. And if you have any further questions or remarks, please do not hesitate to reach out. My email can be found below the pretty picture. Have a nice day.